Hi, I'm Professor Goins. In this video, I'm going to take a look at finding the antiderivative of an inverse function. Meaning, if I know how to find an antiderivative of a function f, can I use that to find the antiderivative of its inverse? What we're going to look at is we're going to look at finding indefinite integrals of a function of an inverse. And of course, the indefinite integral is the collection of all the antiderivatives. Okay. What I'm going to do is I'm going to start by looking at the formula for integration by parts. So as a reminder, the integration by parts formula is this. If I take the integral of u dv, it's uv minus the integral of v du. If you need a refresher on integration by parts, or if you haven't seen that yet, please watch the video that we posted on integration by parts by Professor Van Hamlin. Okay, now let's take a look at this particular integral and let's use the integration by parts formula on it. Okay. This would give me the following. So let's set up the integral here. And for my uv table, again, I need u and I need dv. Once I find those, I can differentiate to find du. And then I can take the antiderivative of dv, that will give me v. As a reminder, u dv incorporates the function expression, in other words, the integrand along with the differential. So that all has to be incorporated, the product of u and dv. dv at a minimum has to have the differential, so dx. And if I put f inverse here, then to find v, I'd have to take the antiderivative, but that defeats the purpose of this. We're just going to go in circles. Therefore, I'm going to put the inverse function here, and then now let's go ahead and proceed by finding du and v. The derivative of the inverse function, I'll start by writing it as f inverse prime of x, and I need some more space here. Looks like I put this too close. So du would be the derivative of the inverse and then dx. Remember, dv was just dx, so that would give me v is equal to x. So there's my integration by parts table. U is the inverse function, and then dv would be dx. Du and v follow from that. All right, integration by parts formula says that the integral of f inverse is, well, it's written as in the format for integration by parts, so I know this is going to be u v minus the integral of v du, and I know what all these terms are in my choice down below. uv is x times f inverse, x times f inverse, minus the integral of v du. That would be, here's v, and then here's du. That would give me x times the derivative of the inverse dx. If you haven't seen how to find the derivative of an inverse, watch the video that I posted where it titled The Derivative of an Inverse Function. But then we're going to use that formula that we developed in that video for this term, for this portion of the integrand. This would give me x f inverse minus the integral of x over f prime evaluated at f inverse. Again, this portion from the denominator is the derivative of the inverse, and if you're not familiar with that, please go back and watch that other video. All right, this right here then, which looks far worse than this, but keep in mind, this is what I want to see if I can find the integral of, and this may be easier, okay? What I'm going to do is I'm going to pick three different functions, three different inverse functions, and work through finding the integral of all three, all right? For example, find the antiderivative of, technically I should say find the set of all antiderivatives, which would be the indefinite integral, or we could just say find an antiderivative and put a specific constant on the end. But I'm just going to leave the sort of abuse the language and say find the antiderivative of, let's say, how do I want to label this? Let's say y is equal to the cube root, b, y is equal to the natural log, c, y is equal to sine inverse. Find the antiderivative of all three of those. Okay. Let's go through the solution. For part A, again, I'm looking for the integral or the antiderivative of the cube root of x. And it's going to be, let's summarize this over here and put it in a box. This formula. Keep in mind, this is overkill for finding the integral of the antiderivative of the cube root, because we can just use a power rule on this. You do not need this for the antiderivative of the cube root, but I think it will be helpful when we come down to some of these harder integrals. All right, now what I have to do is I have to identify the functions. I know that f inverse is the cube root. What else do I need? Well, I'm going to need the function f prime, which means I need f of x. And then I'll need, again, f prime. If the inverse is the cube root, then that means that the function we started with would be x to the third, and then the derivative of x cubed would be 3x squared. So now I've got my f inverse, my f, and my f prime. And really, I don't need f in the formula. I simply need f so that I can generate f prime. All right, let's plug things in. Following the formula that we have listed there, this would be x times the inverse. So x times the cube root minus integral of x divided by, what I do is I take the inverse and I plug that into f prime, meaning I'll take the inverse, which is the cube root, and I'll plug that into f prime, and that's going to go in my denominator. This would give me 3 times the cube root of x squared dx. Okay, let's simplify this. X times the cube root, well, this would be x to the first, x to the 1/3, that would give me x to the 4/3, minus integral, well, that 1/3, I can leave that as a coefficient, and then I've got x over the cube root of x squared, would be x to the 2/3, and then dx. Okay. So I've got x to the 4/3. That 1/3 I can bring outside the integral. And then x divided by x to the 2/3 would be x to the 1/3 dx. Starting back over here, this gives me x to the 4/3 minus 1/3. And then I've got the antiderivative of x to the 1/3. That means power rule for an integral means I'm going to add 1 to the exponent. That would give me x to the 4/3. and then we multiply by the reciprocal of the increased exponent, which would give you 3/4. All right, 1/3 times 3/4, the 3's cancel, leaving you with 1/4, giving you x to the 4/3 minus 1/4 x to the 4/3. These are like terms. I'd have 1x to the 4/3 minus 1/4 x to the 4/3, which gives me 3/4 x to the 4/3. And of course, throughout this whole computation, well, I guess after we did that last integral there, we would have a plus c, plus c, plus c. Okay. So this is the antiderivative of the cube root function, which of course we could have done that very quickly with the power rule, but it gives me some indication of how to then use this formula. Okay? Let's now use that formula for the natural log and then for the sine inverse. All right. Integral of the natural log. We have to identify the, I guess it's not an example, that's solution part B. We have to identify the three functions. What's the inverse, what's f prime? Okay. I know that f inverse is the natural log, that's the integrand that we are working with. F of x then would be e to the x. F prime would also be e to the x. Okay. When I plug things into that formula that I have in that blue box, then this would give me x times the inverse, so x log x, minus the integral of x divided by the f prime evaluated to f inverse, x being the numerator, denominator would be the inverse plugged into f prime, so that means log x gets plugged into e to the x, so e to the log x dx. Inside the integral here, so e to the natural log is the composition of a function with its inverse, meaning they cancel, giving me just x over x dx. Of course, x over x is 1, so this would be the integral of dx. And finally, we get x log x minus x plus my constant, and there's the antiderivative. Okay. Finally, let's do part C, the inverse sine function. And I'll erase this portion because I'd like to leave that box up there. Finally, part C, integral of sine inverse. Okay. Let's identify the functions u, or I'm sorry, not u, f inverse, is sine inverse. That makes f of x the sine function. F prime would then be cosine. So there's my just identification of the functions. All right, now I'm going to plug things into the formula. This would give me x times the inverse of x times sine inverse minus integral of x divided by f prime evaluated at f inverse. So this is f prime, this is f inverse, meaning I take sine inverse and plug it into cosine. That would give me cosine of sine inverse of x dx. Now, this might look worse than the integral we started with, right? Because I've got, cosine of sine inverse in the denominator. We had sine inverse at the beginning, so it looks like we just made it worse. However, there's a trick I can use to change cosine of sine inverse into something much simpler. Let's take a look at cosine of sine inverse. What I'm going to do is I'm going to label sine inverse as theta. So theta is sine inverse. That means that the sine of theta is equal to x. Okay? And what I'm ultimately trying to find then is cosine of sine inverse, which is cosine of theta. Meaning I know sine of theta is x. I want to use that to find cosine. And there's a couple different ways we can do that. Two standard ways are to use a Pythagorean identity or to use a reference triangle. In the video for the derivative of an inverse function, I used a reference triangle. So for this one, I'll use a trig identity. All right, the trig identity is the standard Pythagorean identity. Sine squared plus cosine squared is 1. I know that the sine of theta is x, meaning I'll plug x in to get x squared plus cosine squared is 1. Subtract x squared over, giving cosine squared theta is 1 minus x squared. And then I take the square root, giving cosine of theta is the square root of 1 minus x squared. That will then be my denominator. So when I plug this in, this gives me x sine inverse minus the integral of x over the square root of 1 minus x squared dx. Hope that's on screen. I'll rewrite it on the other side of the board to make sure. Let me summarize where we are. So far I've got this. Integral of sine inverse of x dx is equal to x sine inverse of x minus the integral, and then when I just did the change of the cosine of sine inverse and I plugged in using the Pythagorean identity, I get x over the square root of 1 minus x squared dx. This is the part that I couldn't tell if it was off screen or not. Well, this is a much simpler integral than what we started with, and it certainly looks a lot better than this one, even though they're equivalent. For this one, we can use a u substitution. I identify u as 1 minus x squared. Du would be negative 2x dx. If I look at that integral above, what do I need? There's my x dx. I've got x, I've got dx, I've got a negative there that I could pull on the inside using this negative right here, or incorporating that negative right here. What I don't have is a 2, but constant factors are easy to manipulate. I can put a 2 in the numerator, and then I can pull a 1/2 out front. Okay. This then gives me x sine inverse plus 1/2 integral of negative 2x over the square root 1 minus x squared dx. Again, I haven't substituted in anything, I just kind of laid out the format for it. Then I plug in my u and my du. X sine inverse plus 1/2 integral negative 2x dx is du, and the radicand down here, 1 minus x squared, is u, which gives me 1 over the square root of u du. And of course, 1 over the square root of u, this is the same thing as u to the negative 1/2. And it's easier to see the antiderivative if I use an exponent rather than a radical, especially a radical in the denominator. All right, almost done. This gives me x sine inverse plus a half, and then for u to the minus 1/2 antiderivative, I'm going to add 1 to the exponent, meaning if I take negative a half, I add 1, I get positive a half, and then I divide by the reciprocal of the increased exponent. I'm sorry, I multiply by the reciprocal of the increased exponent, which gives me a 2. Of course, I also have to have a plus c. And then finally, I can cancel the half and the 2, and then I'm going to replace u with the original substitution, giving me the following. X sine inverse plus the square root of 1 minus x squared, and then plus a constant c. This function right here is the antiderivative of sine inverse.